Clear.
Constant speed propellers are daunting to a lot of new pilots out there, but they're not as difficult as you think. That being said, an incorrect understanding or procedure can lead to increased engine wear and damage, so it's important to have a thorough understanding of the system. If you've spent time studying aircraft systems in the FAA material, you'd be surprised to find only a limited amount of information about constant speed propellers. This in turn leaves many students without proper knowledge or understanding of such a somewhat basic yet incredible piece of engineering. Today's video is designed for anyone who's looking to understand the fundamentals behind constant speed propellers. Whether you already have experience with a constant speed or all your previous experience has been in fixed pitch propeller aircraft, you should be able to walk away from this video understanding why we use constant speed propellers and understand the basics of how they operate. A couple disclaimers before we get started. This video does assume you already have a basic understanding of aircraft power plants, as well as a basic understanding of the four forces of flight. So let's first talk about thrust. Thrust is generated from our propeller. The propeller is an airfoil, just like our wings. Therefore, it's going to have all the same elements like a chord line, camber, angle of attack, etc. When we spin the propeller, we are producing lift, but in a forward direction. In other words, thrust is just forward lift. Our propeller blade is twisted. The reason we do this is because the propeller's velocity is different from the root to the tips. The tips are going to move a lot faster, and the roots are going to move a lot slower. As the fuel-air mixture burns in the cylinders of our engines, a piston is pushed downward, causing the crankshaft to turn. Unless your propeller is geared down, your propeller will be directly connected to the crankshaft, resulting in a 1-to-1 ratio between engine RPM and propeller RPM. Since the propeller is a rotating wing through an air mass, it's important to remember that our propeller is always producing drag on itself. For both fixed pitch and constant speed propellers, the resulting RPM on a propeller will always be determined by a balance between the power created by the engine and the aerodynamic drag created by the propeller. When in balance, RPM remains constant. To increase RPM, we need an excess of power from the engine for the amount of drag that's present on the propeller. This excess power overcomes the drag force, allowing the propeller to spin faster until the forces are balanced out again. When decreasing RPM, there is an excess drag from the propeller for the given power on the engine. The excess drag slows the propeller RPM until a balance is achieved. Before we go into detail about constant speed propellers, it is good to review some operating characteristics of fixed pitch propellers. On a fixed pitch propellered airplane, as the name implies, the propeller pitch is fixed. The blade angle doesn't change. When the airplane is stationary, the propeller is at its greatest angle of attack. At full power, the drag created by the propeller significantly prevents us from reaching the maximum RPM on our tachometer. This is because when we are stationary, because the angle of attack is greatest, the drag created by the propeller is also at its greatest. This is why it's important to know the full throttle static RPM for your airplane, which can be found in the POH. We want to know this figure, that way we can ensure our engine is producing full power before we take off. It is not normal for a fixed pitch propeller aircraft to be reaching red line on your tachometer when you are in a static position. As the airplane moves forward, the relative wind changes so that the angle of attack of the propeller decreases. The engine RPM begins to slowly increase. Since we are not achieving maximum RPM on takeoff and climb, we can safely leave the engine at full throttle. Of course, if your POH has something different, always follow the procedures prescribed by the manufacturer. As we level off and accelerate further, the angle of attack of the propeller continues to decrease, meaning induced drag from the propeller is decreasing, and the RPMs begin to increase further. With full throttle and in cruise, we can see that we start to reach the upper limit of our tachometer, towards the red line. In order to avoid hanging out at the red line, or the maximum RPM allowed for our engine, our solution is to reduce throttle so that the airplane's RPM can come back to an appropriate setting. As I've been mentioning, angle of attack of the propeller decreases with an increase in airspeed of the airplane. With the root of the propeller having a slower rotation velocity than the blade tips, washout, or that twist shape, is added to the propeller so that the blade angle of attack is more or less uniform at one specific airspeed and RPM combination. At this airspeed and RPM combination, maximum thrust efficiency is achieved. Here's a visual aid I've drawn out showing the change in angle of attack between the propeller tips and the propeller roots as airspeed increases. Notice how when the airplane is stationary, the propeller root is at a very high angle of attack. So much so that the propeller can oftentimes be stalled while the airplane isn't moving forward in the air mass. As airspeed increases, notice how the angle of attack decreases. Similar to the wing of your airplane, your propeller has a lift-to-drag ratio. At the target airspeed and RPM, you can reach the LD max of your air propeller by reaching this airspeed and RPM combination. Remember from your fundamentals of aerodynamics, LD max is when the airfoil's angle of attack is producing the most amount of lift with the lowest amount of drag. Any faster or any slower, and the total drag forces increase. Again, this is where your propeller achieves maximum efficiency. The drawback, however, since we can't vary the pitch of the propeller, we can only achieve maximum efficiency at one airspeed and RPM. Therefore, we must choose which type of propeller to have that best suits our needs. There are two types of fixed pitch propellers. There's the climb propeller, where the blade angle is low, offering best performance in climbs but slower cruise speeds. And then there are cruise propellers, where the blade angle is high, offering better cruise speeds but worse climb performance. The fixed pitch propeller achieves maximum efficiency at one airspeed. Any slower, the propeller is creating more drag for the amount of thrust it is producing. Any faster, and the angle of attack is simply too low for optimal thrust output. Ultimately, the goal of the constant speed propeller is to make the airplane achieve optimal propeller efficiency at a range of airspeeds, rather than just one airspeed. In a high-performance setting, like takeoff and climb, the propeller's knob is forward, making the blade considered to be in a low-pitch, high RPM setting. In cruise, we want to increase the efficiency of our propeller by pulling back on the propeller knob, which will increase the angle of attack of our propeller blades and decrease the RPM. So the following animations are going to be from Bold Method. They have some very good depictions of how the constant speed propeller works. If you are not familiar with Bold Method, please go check out their site. They are an amazing resource to your flight training and maintaining proficiency in your knowledge. They offer good quizzes, articles, courses, videos, and they are all around one of the best sources for study material. Looking at our components, we have the propeller control knob, which is not labeled. We have the governor control lever, the threaded shaft, the speeder spring, the flyweights, the pilot valve, the prop hub piston and spring, again not labeled, the governor gear pump, and the engine oil. Looking at the prop hub, we can see a piston that has a spring connected to it. The propeller is linked to the piston. The spring forces the piston forward, which forces the propeller blade into a low pitch at all time. Utilizing the principles of hydraulics in that liquids aren't compressible, we can fill the prop hub with oil and push the piston back. As the piston moves back, the angle of attack of the propeller blade increases. If we wanted to reduce the angle of attack on the propeller, we would allow the piston to push the oil out of the prop hub, and as the piston moves forward, the angle of attack of the propeller blade decreases. Now all this occurs due to things happening inside our propeller governor. The prop control lever that the pilot moves controls a governor control lever right above the threaded shaft. The threaded shaft adjusts the tension on the speeder spring. The speeder spring is connected to a pair of flyweights. These flyweights are geared to the crankshaft, and so as the crankshaft spins, these flyweights rotate as well. Under no rotation, these flyweights want to cave inward. However, as they spin, centrifugal force pulls the flyweights apart. Under a neutral, balanced state, the flyweights are in this L shape. In an underspeed situation, the flyweights cave inward, pushing the pilot valve down. In an overspeed situation, the flyweights extend outward and pull up on the pilot valve. The pilot valve is in charge of routing oil either to the prop hub or out of the prop hub. When the pilot valve is pulled up, oil is sent to the prop hub, increasing the angle of attack of the propeller. When the pilot valve is pushed down, oil from the propeller hub is pushed out and returned back to the sump. As the oil leaves the prop hub, the angle of attack of the propeller decreases. The driving force between the pilot valve's movement is based on a balance of forces between the speeder spring's tension and the flyweight's centrifugal force. When these forces are balanced, the pilot valve remains neutral, and it does not allow oil in or out of the prop hub. When there is an imbalance of forces between the speeder spring and the flyweights will either swing outward or they will swing inward. When they are balanced out, the L-shaped flyweights will remain in this position. As you pull the blue knob back, you are releasing tension on the speeder spring. As that happens, there becomes an imbalance between the speeder spring's tension force and the flyweight's centrifugal force. This will cause an overspeed situation on the propeller. The flyweights swing outward, pulling up on the pilot valve. Oil will be pumped into the prop hub, pushing the piston back and increasing the angle of attack of the propeller blade. As the propeller blade angle of attack increases, so does the induced drag of the propeller. This is what slows the engine RPM down. As the engine RPM slows down, your flyweights will return to their neutral L-shaped position as the centrifugal force balances out to the new speeder spring tension. Pushing the blue knob forward increases the tension of the speeder spring. This disrupts the balance between the speeder spring tension and the centrifugal force of the flyweights. Because the speeder spring is increasing in tension, the engine is considered to be in a low RPM situation, the flyweights will go to an underspeed condition, where the flyweights move inward and push down on the pilot valve. As the pilot valve moves down, oil from the prop hub is pushed out by the piston inside the prop hub. That oil is pumped out and returned to the sump. As the piston moves forward, the angle of attack of the propeller decreases. This decrease in angle of attack reduces the induced drag of the propeller. As the drag decreases, the RPMs will increase. As the RPMs continue to increase, your flyweight centrifugal force will increase as well, until a balance is achieved between the flyweight centrifugal force and the speeder spring tension force. Now, the propeller governor is always working, even when we are not messing with the blue propeller control knob. For example, let's think back to our fixed pitch propeller from earlier. If we increase throttle on our fixed pitch propeller, the RPMs increase. If we pull throttle back on our fixed pitch propeller aircraft, the RPMs decrease. Increasing throttle forces the engine to want to increase its RPM. The added power from the throttle puts the propeller governor into an overspeed condition. Our flyweights extend out, pulling up on the pilot valve and sending oil to the prop hub, where the propeller angle of attack is increased. Once again, as the angle of attack of the propeller increases, so does the induced drag, which slows the RPM back down. As the tension force and the centrifugal force of the speeder spring and flyweights respectively equalize, the pilot valve will then return to neutral as the flyweights return to neutral. On the flip side, if we reduce throttle, normally engine RPM would decrease. This puts the propeller governor into an underspeed situation, where the flyweights swing in and the pilot valve is pushed down. As the pilot valve is pushed down, oil from the propeller hub is pushed out and returned to the sump. The piston moves forward, reducing the propeller's angle of attack. Again, as the angle of attack is decreased, so does the drag. This allows the propeller's RPM to increase until the flyweights return to a neutral position because the centrifugal force from the flyweights and the speeder spring tension forces equalize. Again, thinking back to our fixed-pitch propellered aircraft, if we kept throttle where it was at and we just lowered the nose to increase our airspeed, propeller RPMs would increase as well. This is due to the reduced angle of attack of the fixed-pitch propeller. With the reduced angle of attack, there's less drag and the propeller RPM increases. In a constant speed propeller, the same thing occurs, however, the propeller governor steps in and behaves in an overspeed condition. Once again, the flyweights extend outward because there's an imbalance of force between the centrifugal force of the flyweights and the speeder spring tension. As the flyweights extend outward, they pull up on the pilot valve, oil is sent to the prop hub, pushing the piston back, increasing the angle of attack of the propeller. As the propeller angle of attack increases, the RPM decreases. As the RPM decreases, the centrifugal force on the flyweights decreases until the forces match with the speeder spring tension force. Likewise, if we put the airplane into a nose-up situation, a fixed-pitch propellered airplane, engine RPMs slow down. In our constant speed propeller, the propeller governor sees this as an underspeed condition. The flyweights swing in, allowing oil to escape out of the prop hub and lower the angle of attack of the propeller. As the angle of attack is lowered on the propeller, the flyweights will return to their normal neutral position as the RPMs increase and the centrifugal force of the flyweights pulls them back to a neutral position. It's important to note that variations in airspeed and variations in throttle will result in changes with your propeller governor. However, these changes will happen so quickly you should not necessarily see a change in RPM on your tachometer. The only exception would be if you've made aggressive power changes or aggressive pitch control movements where a momentary rise or momentary decrease in RPM might be expected. If this occurs, this is normal. This is your governor just taking a second to catch up. In-flight, large power reductions, such as power to idle, means you might not be supplying enough power to the engine to sustain the desired RPM. When this occurs, the airplane has gone to the full low pitch setting and there's still not enough power to the engine to achieve the desired RPM setting. As always, follow POH procedures to ensure that you are not operating outside of the limitations of the engine's RPM and manifold pressure settings. As far as operating with a constant speed propeller versus a fixed pitch propeller, there are some minor differences. Yes, of course, you obviously have the blue knob as an extra engine control lever. However, this blue knob does not affect the engine's power output. That is still only controlled by the throttle. With the blue lever, you are only controlling engine RPM. So let's compare the differences between a fixed pitch propeller operation and constant speed propeller operation from startup to shutdown. During startup operations on a constant speed propeller, you want to leave the propeller lever into a high RPM full forward state. By doing so, we're commanding the propeller to have high RPM, therefore the lowest resistance or drag as the motor gets started. Once the engine starts up, you'll find that throttling around like you normally would in a fixed pitch propeller airplane is more or less the same with a constant speed propeller. Normal ground operations usually don't have high engine power, which means we're not putting enough power to the airplane to supply the maximum RPM which we have selected with our high RPM setting with the blue knob. So, taxiing around should be relatively easy. Should be relatively straightforward to what you're used to with a fixed pitch propellered airplane. Once you get to the run-up, one more procedure is going to be added to your checklist, and that'll be a propeller governor check. Usually, you will cycle the propeller 3 times. On the first pull of the propeller knob, you will look for a rise in manifold pressure and a drop in RPM. Once you see the RPMs decrease and the manifold pressure increase, you will push the propeller knob back into a high RPM setting. Once the engine stabilizes, you will cycle the propeller knob again. On the second pull, you're looking for a drop in oil pressure. The oil pressure should not drop below normal operating requirements. As you see the oil pressure drop, increase the propeller RPM back to a high RPM setting. On the third pull, you're going to be looking at the propeller hub area in the cowl. During the cycling of the propeller, this is the first time you are sending oil to the prop hub for the flight. This is the time to look for any leaks that could be coming out of your propeller hub. So on the third pull the propeller knob all the way out, verify there's no oil spitting out from the propeller hub, and then push the propeller lever back in. Upon completion of your 3 cycles, you have verified that the propeller governor is operating as it should and that there are no leaks in the propeller hub. For takeoff, you're going to continue to leave the propeller knob set to the full forward, high RPM, low pitch setting. This will allow you to achieve maximum performance on your takeoff. As you apply takeoff throttle, you will verify that the RPMs are at or near the maximum allowable RPM, or your red line. As you are on your initial climb out, you will then readjust your power settings for the takeoff power configuration as specified by the POH. Sometimes this entails reducing throttle to a maximum manifold pressure, followed by reducing RPMs just below maximum allowable RPM. Ultimately, follow the POH. As you transition into cruise, you're going to set cruise power. Your cruise power is going to be determined by, again, your POH's performance tables. You're going to lower manifold pressure to the desired setting, followed by lowering your RPMs to the desired RPM setting. When we are reducing power to the engine, we want to lead with throttle and then follow with the RPMs. So decreasing power starts with decreasing throttle, then decreasing RPM. On the flip side, let's say we want to go back into a climb. To enter a climb, we want to lead with propeller. So we will increase the propeller lever to the climb RPM setting, and then follow that with setting the throttle to the desired climb manifold pressure. As you continue to go up in altitude, you will notice your manifold pressure continues to decrease. This is normal. The manifold pressure gauge also reflects the decrease in air pressure the higher altitudes you go. Following the power management techniques as described will allow you to maintain higher RPMs than your manifold pressure. In most cases, you will fly with the RPMs at a higher value than the manifold pressure. Obviously, your RPMs are going to be in the thousands, for example, 2,500 RPM, as opposed to 25 inches of manifold pressure. For the sake of this argument, ignore the zeros after your RPM. We will call 2,500 RPM and 25 inches manifold pressure the same. The reason it is a general rule of thumb to keep the RPMs higher than your manifold pressure is so that you avoid excessive engine wear and damage. Having high manifold pressure means you are increasing the fuel-air mixture going to your engine. This increased fuel-air mixture is producing more power inside the cylinders. If you were to operate with a high manifold pressure and a low RPM, the low RPM is adding resistance to the engine movement. In other words, high manifold pressure, low RPM has the airplane fighting against itself. A good analogy here is manifold pressure is like our legs pumping on a bicycle. RPMs can be considered like the gear that we are operating our bicycle on. If I want to climb a mountain, I want to go to the low gear and pedal fast. If I want to climb my airplane, I want to go to the high RPM and go to a high manifold pressure. If I'm on my bike and I'm no longer climbing my hill, as I increase speed, I can reduce the amount of pressure, the amount of work that my legs are doing by reducing throttle in the airplane. I can also go to a higher gear on my bicycle or a lower RPM, which will achieve greater efficiency. Flying your airplane with high manifold pressure and low RPM is like riding your bike, pedaling really, really, really hard up a hill in a high gear. Now, there are certainly exceptions to that rule where you can, in fact, operate your aircraft with higher manifold pressure and a lower RPM. This will only be determined by the specifications laid out in the POH. If you are adjusting your power and you're ever unsure, as a good rule of thumb, always keep the RPMs higher than your manifold pressure. Occasionally, you might also hear other pilots out there talk about a power setting as a squared number. For example, you might hear the term 25 squared. What they mean by that is they're flying at 25 inches manifold pressure and 2,500 RPM. Anytime the RPM and manifold pressure match, that value is considered squared. Generally, as you start your descent, you can leave your propeller lever where it's at and just reduce throttle like you normally would in a fixed-pitch propellered airplane. As you enter the traffic pattern and prepare for landing, you will adjust your propeller knob all the way forward to a high RPM setting. It's important that we do this as a before landing check and not as an approach check. We don't want to operate the engine at redline for long periods of time. So do this as you are nearing the final approach. The reason we go to the high performance setting for landing is in case of a go-around. All we have to do is increase throttle to the takeoff setting. Once you've landed, the propeller knob is all the way forward still, and you can once again taxi the airplane just as if you would a fixed-pitch propellered aircraft. As you shut down the airplane and oil pressure is lost, the propeller will go to a fine pitch setting. And just like that, a normal flight is accomplished with a constant speed propeller. Fairly simple, right? On the topic of emergencies, it is important to know how your propeller hub is laid out. On most single-engine piston aircraft with a constant speed propeller, the piston is laid out just as it is here in bold method. By having this layout, a loss in oil pressure means the piston will push oil out of the prop hub and the propeller will fail to a low pitch fine setting. This low pitch setting will increase the drag of your propeller disc. Some aircraft reverse this design so that in case of an engine failure, the propeller fails to a high pitch setting. There's a term that you've probably heard called a feather. The blade angle is increased so much so that the windmilling propeller slows to a stop in flight. This decreases drag. The reason that some aircraft do this is because on a multi-engine aircraft specifically, if you had an engine failure, the drag created from an unfeathered propeller could be detrimental to maintaining aircraft control. And so by failing to a feather, the aircraft remains under better control with asymmetrical thrust and asymmetrical drag from the failed engine. So there you have it. You have a constant speed propeller. It's a simple but also complicated system, something that's not really highlighted well in the FAA, in my opinion, but something that is crucial to your understanding in your aircraft operations. I hope you found this video helpful in your studies. And so with all that, I want to thank you so much for watching. My goal with these YouTube videos is to help as many pilots out there remain safe, knowledgeable, and proficient in their aircraft operations. If you found this video helpful, please give this video a like and share it with someone you think who might benefit from it. If you have another topic you'd like me to cover, please leave it in the comments below. And with that, thank you so much for watching, and we'll see you in the next one.
Clear!